Okay, so today is the second part of AFM modes topic, and we will mostly focus on magnetic force microscopy and high-speed atomic force microscopy. I will also mention electrochemical AFM and piezoelectric with Kelvin probe force microscopy as well. Most of these techniques that I will be talking about today, they can utilize single pass and dual pass technique. So first of all, I'll just tell you a couple of words what is single pass and dual pass methods in general. Additional measurement modes are usually often combine not only topographic measurements, but also they have special type of the cantilevers that allow them to measure the sample properties beyond the topography itself. So we will discuss this kind of measurements today, for example, magnetic force microscopy or different electrical AFM modes. So key thing in such measurements is to separate the short-range van der Waals forces from longer-range electrical and magnetic forces. So what we utilize is the so-called lifting mechanism that enables to probe the longer-range electrical and magnetic forces, and then it helps us to deconvolute them from the short-range van der Waals that are present during topographic images. So the height that we use to lift the tip over the sample is often a parameter that has to be optimized by the user in order to get the successful imaging. And usually varies from few nanometers to hundreds nanometers, depending on the range that you're interested in. And the lifting can be done in so-called single or interlaced and dual scanline modes. So on the left-hand side here is a single pass, like a group of single pass methods or constant height setup. When the slope of the surface is measured from a completed topography image or line before the imaging of the long-range interaction is started. And so we go one time across the sample, then we lift, and then the tip is scanned at fixed height above the sample, compensating the average slope going backwards. Dual pass modes is an alternative to single pass. And what they do, they provide the topographical information of the surface along with the functional signal. So in interlaced mode, the forward pass records the topography of the sample. And then the tip is lifted like above the sample during the backwards pass. In dual pass topography, so it is like the same place is measured two times, like forward and backward. And while we're going backwards, we are detecting the long-range signal. So interlaced mode is a bit faster than general dual pass method because here we are touching the sample, and as probably you remember from previous lectures when I was talking about contact modes, I was telling you that the contact mode is generally like faster than like dynamic modes and so on. So here we have the same thing, that interlaced method is a bit faster than general dual pass method, because in general dual pass method the the tip goes along the sample and then is being lifted and then going along the sample about a certain distance, and then this procedure is repeated like twice. Okay, so these are like general introduction of single and dual pass methods, and I will be giving you some of details along the story. So let's start with magnetic force microscopy, or shortly MFM. Here you have just two examples: a metal evaporated videotape on the top and a hard disk manufactured by IBM at the bottom. So these are one of the very, very early applications of magnetic force microscopy. And it was related to understanding the magnetic patterns on data storage media. It can be magnetic hard disk, it can be magnetic tapes, magnetic optical disks, and so on. And so these are, so for example, here, the hard disk is an excellent example because in general, hard disk drives are extremely flat. So they can be like polished coated surfaces, and so topography is not likely to show too many features beyond like scratches that come from normal wear and tear. And the magnetic media is usually slightly below the top surface, and it's an ideal sample to try looking for magnetic contrasts. Here on the left-hand side is a topographic image of the hard drive, and not surprisingly, you don't see many features here. And on the right-hand side, at a certain lift-off distance, when the frequency shift is plotted, you can actually see very clearly the bit patterns that are written on the hard disk media, as over here. The same situation is in metal evaporated videotape. So on the left-hand side, you can see a topographic image with the metal particles on the surface of the tape. And here you do not see any pattern at all. But on the right-hand side, when you use magnetic force AFM, you can see basically the magnetic fields and the information that is written on this tape. So coming back to physics, so in classic AFM, we usually operate in Lennard-Jones model. And in usual AFM, the forces are not long-range forces, and the attractive force basically tailing off very, very quickly, starting from 10 nanometers above the surface, and the force sharply drops down at this range. But magnetic force is so-called long-range magnetic force, and for magnetic dipoles, the force drops a bit slower. Even though, if you can see here on this graph, it drops quite quickly as well. But in comparison with van der Waals forces, we still have a bit of the room, as you can see here. So this is just like a general reminder about the forces that we're using. So as I've already said, magnetic fields and forces also decay quickly with the distance. So in order to measure local properties, the probe must be quite close to the surface. So that's why we still use atomic force microscopy with a bit of modification, and we call it magnetic force microscopy. So in this mode, the presence and the distribution of magnetic fields is measured directly using a magnetic probe. Typically, a magnetic probe is standard cantilevers made from silicon with a very thin magnetic coating. I will talk about types of the cantilevers a bit later. So typically materials that we use for the coating include cobalt nickel, cobalt chromium, and the addition of such coating can have like two effects on the cantilever. Firstly, these materials are typically softer than underlying silicon, and this may increase the wear rate. And the second, any coating added to the end of the tip will increase the radius of the tip. So as a consequence, the resolution of the experiment drops down a bit. So typically, magnetic forces, they lay in orders of magnitude lower than other tip surface forces when in contact. So it is useful to measure them when the tip at a certain distance, from the surface. So usually it's about from 5 to 50 or maximum 100 nanometers. Because when we lift the tip, we are reducing the interference from short-range forces. So the question is, what does MFM really consist of? What one is trying to do with an AFM is to measure stray magnetic fields that come out of a magnetic medium or a magnetic sample. And so when a tip is brought at a certain height above from the surface, it experiences these gradients, as you can see here. So it experiences the gradients, and those are typically sensed using changes in amplitude or changes in phase or changes in frequency. So now the point that I want to emphasize, well, there are 2 points that I want to emphasize here. First one is what is different about the force gradients generated by magnetic samples compared to electrostatic or other samples. So it is the fact that the gradients need to be they do not need to be all-time attractive, like in case of electrostatic, or all-time repulsive. So as you can see here, it can be different directions, and they can actually change depending on the interactions between the tip and the sample. Another thing that I want to emphasize is that magnetic force microscopy refers to the particular case when the tip has a permanent magnetic movement. So in other words, it's basically a permanent magnet at the end of the tip. And so the idea is you have these magnetic fields, let's say, denoted by a vector H, and the tip comes in, interacts with this magnetic field H, and you need, of course, very good models that allow you to couple or to understand the connection between the force applied on the tip and this magnetic field H. So the important thing about magnetic force microscopy is that even if one is able to back out the force gradients that cause the shift in frequency, it turns out that well, there is not a unique one-to-one relationship between the measured magnetic field and the actual micromagnetic pattern on the surface. And it turns out that multiple patterns that can actually give you it turns out that there are multiple patterns that can give you the same frequency shift or force gradients. And this is again something that needs to be taken into account. And this is why when one deals with magnetic force microscopy modeling, the interaction of the tip with magnetic fields and understanding the connection between the structure of the media and the magnetic fields are very essential to interpret the whole image correctly. The measurement of this resonant frequency of the cantilever is known as a dynamic mode AFM. Oh, sorry, not AFM, MFM, magnetic force microscopy. And in this mode, the cantilever is usually forced to resonate and the amplitude about 10 to 30 nanometers. And it enables the accurate detection of very small frequency shifts that are possible. So typically the shifts are about 3 hertz to 80 kilohertz. And in this mode, a control circuit is needed, which matches the beat frequency of the actuator and drives the cantilever with the actual resonance frequency. And very often we use a phase-locked loop, or abbreviation is PLL, phase-locked loop circuit. And what it does, it keeps the phase difference between the driving signal and the measured deflection of the cantilever at approximately 90 degrees. So this control circuit adds an additional noise to the measurement of signal because of that. And for small signals, sometimes it is still preferable to fix the frequency of the driving signal and then measure the phase difference between driving signal and measured cantilever deflection. So the phase shift, which is in the order of few degrees, strongly depends on the damping of the cantilever, and it will be turned out as a function of many parameters. So again, to summarize everything here, magnetic force microscopy usually is used in dynamic mode with phase contrast, and cantilever has a thin magnetic coating, and it will be driving near its resonance frequency. Then yes, so the cantilever will be predominantly respond to out of different fields that are occurring at the sample surface. Okay, so let's go to the next slide where I'll talk a bit about the type of the tips. So these are like some of the interesting specifics about how a magnetic force microscopy works. Well, first of all, as I mentioned to you, we need to have a permanent magnet at the end of an AFM tip. So these days, this is done by coating a fair magnetic material, a permanent magnet effectively at the end of the tip. So this is usually a combination of cobalt chromium or sometimes nickel iron tips. And you can purchase these MFM tips from like many vendors off the shelf, and you can actually get them with different amounts of this permanent magnetic moment associated with each tip. So you can get them in low, medium, or high values of magnetic moment or coercivity of the tip. It depends on your applications. And the reason why this choice is provided is because, as most of you know, when you've got data stored on a magnetic medium or magnetic patterns written on a medium, if you apply a very large magnetic field, you can actually affect these particular sample that you're looking at. And you probably know, if you ever seen for example, a magnetic tape, and if you ever brought a magnet in front of the magnetic tape, you can actually erase the magnetic patterns, so you cannot like listen to or see anything afterwards when you play this tape. So in a similar fashion, what you ideally want to use is a tip that does not perturb magnetically, or does not perturb like the magnetic domains or magnetic moments of the sample that you are trying to image. So you want to have a low cursivity or like low magnetic moment tips. On the other hand, the interaction forces and the force gradients depend on the magnetic moment of the tip. So if you have very small magnetic moments of the tip, you get smaller forces and smaller gradients, and therefore you don't see much. So there's a funny choice of magnetic force microscopy tip that involves an interesting compromise between wanting a high signal to noise ratio, but at the same time not wanting to actually disturb the magnetic patterns of the sample that you try to see. So the tip magnetic moments needs to be chosen depending on the softness of the magnetic material of the sample and so on. Okay, let's talk more about the actual image over here. So as you already know, most scanning probe microscope tips are very pointed and very sharp. And that's what we're talking about when I presented tunneling microscopy for you, and AFM tips. They are all atomically sharp. And you might also assume that MFM, magnetic force microscopy tip, should also have the shape of a sharp needle. However, what we are interested in is not the topography. We're interested in long-range magnetic forces. So here is the actual comparison of two different tips. So this is like a sharp point versus a bar type MFM tips. So the width of the base of the triangular tip is adjusted in such a way that the maximum signal of the both tips are equal. Here and here is equal force. So the fact is that the bar shape is the optimum shape for MFM. And so in this type of tip, all magnetic charges are located in the front surface on the bar and as close as possible to the sample surface. And therefore, all magnetic charges contribute equally, equally well to the signal. In a pointed MFM tip, the charge is distributed over the complete tip, and the charges located further away from the sample still contribute to the signal, but the effect is stronger at longer wavelengths. And if the maximum signal of a pointed tip or a bar type tip is set equal, the bar type tip will perform better at high spatial frequencies and therefore show better resolution to you. And of course, when the wavelength approaches the gap zero of the bar tip, the pointed tip will perform a bit better. But you always can tailor the bar type tip in such a way that this happens at the wavelengths above the critical value. So for example, like as it's indicated here. So you can also argue that you can allow the pointed tip to have high signal at low spatial frequencies by increasing the tip length. This, however, does not significantly increase the signal at high spatial frequencies. So of course, I don't don't want you to think that the magnetic tips, they are like very thick and they look like a huge bars. No, no, no. They're still quite sharp, as you can see here. And in the early days, they were not like they were doing a case by case basis. So they were not like mass production of this kind of tips. But here you can see the photo of actual magnetic tip, and this end is how people try to solve this problem with the sharpness of the tip and the distribution of different charges along the tip. So that's why we need like different coatings on the tip and so on. Okay. Let's talk a bit about dual pass technique in magnetic force microscopy. So another interesting feature of magnetic force microscopy is that it's important to separate the topography of the sample from the magnetic force information, and this thing is done in two ways. First, it is done by taking a topography image in the first scan. So in this case, we use either contact mode AFM or tapping mode AFM, or like tapping mode AFM with repulsive regime, or even frequency modulated AFM and the repulsive regime. So any modification of AFM technique will work to get the topography first. And this has the effect of making sure that the topography image is acquired in the mode where most of interaction forces actually come from the contact. So it can be van der Waals forces or from the contact elastic forces, and very little contribution comes from magnetic side. As a result, you can expect the topography image, if done properly, it will not have any information about magnetic interaction. And on another hand, when you lift up off the surface, so let's say you've gotten a topography image using your first scan, you would lift off and then move the Z piezo actuator as up, and in the manner to mimic the measured topography of the sample. So it will go the second time here mimicking the overall topography, and so you're following effectively the cantilever now at the fixed height from the sample. And because you're basically setting your Z motion by a fixed distance from the measured topography of the sample. Now, what this allows you to do is the forces you end up measuring at an offset distance must be longer range forces, which must arise from magnetic interactions. So magnetic force microscopy is typically done using this two-pass technique, where a topography is first measured and effort is put into making sure that magnetic information doesn't reside in the topography information. And then the second pass at a certain offset can be used to detect the force gradients. The question is, what do you measure? What are the observables when does the second pass? And this depends. There are many studies using many different techniques. One, you could do the second pass with the phase lock loop, PLL, that I was talking about like 2 slides earlier. So what you do the second pass with phase lock loop turned on, and you may want to do that in the situations where you want extremely high sensitivity and you want to detect very slight changes in resonance frequency due to magnetic interactions. So if you use a phase lock loop and do the second pass, you have to keep in mind that the second pass, that in the second pass there is no feedback on Z involved in it. So Z follows a certain pattern here, right? Certain pattern as you move up and down. So as a result, the observable in that case becomes a frequency shift. So remember, we're not using the frequency shift here to do a Z topography feedback. Rather, we simply measure this frequency shift at certain fixed height above the topography from the sample at at every point in the sample. So in that case, the observable will be frequency shift, and often frequency shift can be acquired at different Z distances from the substrate, different Z distances here, or in other words, different lift-off distances. You can also do the same second pass measurements without phase lock loop or PLL. And if you do that, the amplitude and the phase of oscillation are going to change because the excitation frequency is fixed and the resonance frequency shifts. Both the amplitude and phase are going to shift, as you can see on this image. And people choose to either plot the amplitude signal or the phase signal in the second pass. But like when we look at what is called magnetic force microscopy images, they are basically images of either frequency shift at certain lift-off distance over the sample or phase of oscillation at a certain lift-off distance from the sample, or it's like they can be amplitude of oscillation at certain lift-off distance from the sample, depending on whether or not phase lock loop is used in the second pass. And as I mentioned, it's really like whenever you see a magnetic force microscopy image, it refers to these observables made in the second pass. So let's move further to the applications. And here is an example where MFM is used towards the applications of biology. So these days, there is a lot of interest in magnetic nanoparticles. So these are the particles that typically have diameters less than 50 nanometers or so, and they're being used for all sorts of applications, from labeling cells, tagging cells, cell sorting, to actually being used for like novel cancer therapy methods and so on. What's interesting about trying to do magnetic force microscopy about such particles is that when you're dealing with magnetic particles that are so small in size, it turns out that the magnetic moment inside them is it is not fixed, but flips back and forth just due to energy from the environment at room temperature. So they don't have a fixed moment anymore, and they flip back and forth. And in order to get a fixed magnetic moment out of these particles, one needs to apply an external field, either vertical or horizontal field, depending on the configuration of the system. And it's only after you do that you can hope to get a signal in AMFM image. And what you can see here on this image is a selective modulation of different magnetic domains that can be accomplished by applying alternating current to a solenoid placed under the sample stage. So just for those who are not very familiar, what is alternating current is abbreviated as AC. It is a current which periodically reverses direction and changes the magnitude continuously. So this is like the opposite to the direct current, or DC, which flows only in one direction. So when you apply this alternating current, magnetic nanomaterials will vibrate according to the amplitude and strength of the applied field. And the tip that is scanning in continuous contact with the sample can be used to detect this vibration of magnetic nanomaterials. So images obtained by this technique can visualize how magnetic nanoparticles, or for example metalloproteins, so it's a protein that contains some sort of metals in it, they can respond to the flux of the applied alternating current, or like electromagnetic field. And the results with this technique demonstrate new possibilities for AFM imaging of magnetic materials, for example, such as ferritin, and it allows to measure it with exceptional sensitivity. So ferritin is a spherical protein with iron inside, and basically it has ferromagnetic core, and it's weakly paramagnetic. And so this kind of protein is oftenly used in different magnetic force microscopy studies. So I will talk about this on the next slide. So let's talk about this picture first. So this is like so what we see here is a method of the bottom-up assembly of biomolecular structures that combines the precision of the atomic force microscope with the selectivity of DNA hybridization. So here we have functional units coupled to DNA oligomers, and they are being picked up from a depot area because of we have two strands of DNA that are complementary to each other. And then so one DNA strand is attached to the surface, another DNA strand is attached to the tip of the cantilever. So these units can be transferred and deposited on a target area to create different geometrical structures. So this kind of technique is called cut and paste process. So, and this can be done many times. So in A, we have object picked up from the discrete storage, and then it is being deposited with a quite precision at point B, and then the length and the binding energy of oligomers that are used in an anchor or a handle are chosen in a way that the unbinding forces allow to get them away and then repeat the procedure. And then this kind of technique can be used to place single proteins in a very precise way and run different biochemical reactions. So for example, if the circle and the cubes here are different enzymes, if you place them close enough to each other, there will be a chemical reaction happening here. And the theoretical detection limit of this conventional magnetic force microscopy is about 15 nanometer. But of course, in practice, it's a bit bigger. Okay, and then this is the question: is how we can actually make it very precise. So now let's look at the right hand side and the bottom of this slide. Like the sensing ability of conventional magnetic force microscopy strongly depends on the shape and magnetic property of the probe itself. So again, as I've already told you, the magnetic force microscope probes or tips are coated with magnetic materials, and this layer usually broadens the tip radius from 5 to 10 nanometers to 20 to 50 nanometers. So it leads to a lower spatial resolution in the topography images in the comparison with usual AFM probes. So how we can enhance the properties of magnetic tips? We can functionalize them with different nanoparticles or nanotubes. And here, researchers used metal nanoparticles, magnetic nanoparticles, at the distance where non-magnetic interactions do not interfere. And this is just the example how you can manufacture these highly sensitive probes. And this particular approach enabled to place a single ferritin protein molecule at the very, very end of AFM tip. So again, what is ferritin? It is a protein that has iron ions inside. So in terms of the sizing, the protein itself is about 12 nanometer size, like the outer shell, and the inside cavity is about 8 nanometers. So it can accommodate up to 4,500 iron ions. And what you can see here, here you can see the picking up an avidin ferritin conjugate. So to pick up a single conjugate, the difference between the unbinding forces of complementary DNA that is used here and the avidin binding interaction should be addressed quite carefully. And here again, you can see that DNA is widely used to place the probes in a very precise way. And in the bottom, you can see a topographic and corresponding magnetic image of magnetic nanoparticles that are scanned with a reduced iron tip. So the vertical height of these particles was measured to estimate the size, and these line profiles, you can see, so the size of the magnetic particle is about 9.5 or so nanometers, and each particle also causes the magnetic field here that also can be detected. Okay, so I think this is all for magnetic force microscopy, and let's move to electrostatic force microscopy. So this is analogous to standard magnetic force microscopy, except that the gradients that we sense are happening due to electrostatic rather than magnetic forces. So in both methods, the cantilever is vibrating near its resonance frequency, and we use piezoelectric element as well. So the cantilever's resonance frequency changes. So it changes in response to any additional force gradient. And attractive forces make the cantilever effectively kind of softer, and then they reduce its resonant frequency. And the repulsive forces, they make the cantilever kind of stiffer, increasing its resonance frequency. So this is what is depicted here. So the best candidates for electric gradient images are samples that have large contrasts in electric force gradient, and for other samples that have rough surface topography or small voltage variations, this technique may be not the best one. So we use electrostatic force microscopy to map electrical properties of the sample. And what it does, it applies a voltage between the tip and the sample while the cantilever is oscillating above the surface without any contact. And during the scan of the sample surface, these forces lead to change of this oscillation amplitude and phase. We can use oscillating like metal coated AFM tip to measure or map different local charges on the surface. We can be interested in local dielectric constants. We can measure film thickness of different insulating layers. And we can be interested in the photo-induced voltage or different contact potential differences. So this is about electrical force microscopy. And now we will talk about Kelvin probe force microscopy, or KPFM. So it was introduced as a tool to measure the local contact potential difference between conducting atomic force microscopy tip and the sample. So mapping the work function or surface potential of the sample, it can map it with a quite high spatial resolution. Since its first introduction, KPFM was used extensively as a unique method to characterize the nanoscale electronic or like electrical properties of metal surfaces or semiconductor surfaces and different semiconductor devices. And recently it has also been used to study the electrical properties of organic materials or devices and even biological materials. So again, what it does, it measures the difference of contact potential. So contact potential difference is abbreviated here as CPD. So this difference is between the sample surface and the tip. And in high resolution KPFM, CPD is strongly affected by a short range force between tip and sample. So this contact potential difference is associated with short range force and is specifically referred as so if it is affected by short range force, it will be referred as the local contact potential difference, or LCPD. So again, for the high resolution KPFM, understanding this fundamental difference between CPD and LCPD is critical. And it is important to know how they correspond to physical properties of the surface. Here we have phi of the tip and phi of the sample. So here is like S is sample, T is tip. So these two phis are the work functions of the sample and the tip. And E here is the electronic charge. So when an AFM tip is brought close to the sample surface, an electrical force is generated between the tip and the sample surface because of the difference in the Fermi energy levels. And here it shows the energy levels of the tip and the sample surface when they are separated by the distance d. So this part, it belongs to the tip, this part belongs to the sample, and there's distance d between them. So they're not electrically connected. So equilibrium requires these Fermi levels to line up at a steady state, and if the tip and sample surface are close enough for electron tunneling, so we will have this effect here. And upon the electrical contact, these Fermi levels will align through electron current flow, and the system will reach the equilibrium state, which is shown here. So here the tip and sample surface are charged, and we have some voltage of CPD. So CPD again is a contact potential difference, and it is going to form, and the electrical force will act on the contact area due to this effect happening. And on the right hand side, so again DC is a direct current, the constant one that goes in one direction. So here the force can be nullified. So here we have the break, and if we apply external bias, so the voltage of the directed current, so it will have the same amplitude as the voltage of the contact potential difference, and will go in an opposite direction. So that's why the applied voltage eliminates the surface charge in the contact area, and the amount of applied external bias will nullify the electric force. So the work function of the sample can be calculated when the tip work function is basically known as shown before. To summarize all of this, is that the electrostatic interaction takes place mainly between the tip apex and sample surface, and the spatial resolution is approximately equal to the dimension of the tip apex. So these electrostatic interaction from the sample includes both the tip and the cantilever, and that brings the spatial resolution. So that's how these effects between the tip and cantilever can influence the spatial resolution of the imaging experiment. So it is good to know that KPFM itself can be performed in a single pass technique and in dual pass technique. So single pass KPFM obviously will give us faster imaging process and will provide some additional information from the cantilever's response at quite high harmonic frequencies. And dual pass KPFM is usually used to minimize crosstalk from topography effects. So in the same way as electrostatic force microscopy, the first pass is acquired topography in the tapping mode, and the second pass will work with the conducting tip and all the electrostatic forces. And HD KFM is the modification of KPFM, and it has a much higher sensitivity and resolution. So, and usually one of the clear advantages of the single pass approach in comparison as double pass implementation is the enhancement of resolution and sensitivity, because the tip remains in a non-contact regime, but also is much closer to the surface, as illustrated here. So this is standard one, and this is high HD KFM, so it's much closer to the surface in comparison with the standard one. And here's the direct comparison between two techniques. So here we're taking the scan of the graphene sample, And the contact potential images that we obtain in a single pass setup provides better contrast and lateral resolution of the graphene domains. And this is due to the fact that in a single pass approach, the tip is oscillating closer to the surface, typically 0.1, 0.3 nanometers, or even touching the surface intermittently, and in comparison with the double pass mode or lift mode, which is typically above the surface about 10 to 20 nanometers. So this is how we can increase the resolution as well. Okay, and now let's go to the applications of electric force microscopy in biological studies. So here is an example of guanine-based quadruplex DNA. So just a general reminder, usually DNA is double-stranded, right? And it has hydrogen bonds between strands. If we have a pair, guanine, cytosine is 3 hydrogen bonds. If it's adenine and thymine, has 2 hydrogen bonds. Sometimes DNA can form this kind of structure called quadruplex when it has regions with a lot of guanine in a row. So these kind of quadruplexes, they are usually regulatory elements, and they can be found in telomeres, for example. So electrostatic force microscopy can be used to study the electrical properties of different types of quadruplex DNA. So this one is a tetraquadruplex because it has 4 separate strands, and this is like intramolecular quadruplex because it is only one strand that can form similar structure. And these intramolecular quadruplex usually has to be stabilized by positive metal ions. Usually it is potassium ion. And the environment, like the buffer which is surrounds these kind of DNA, is very important because as you can imagine, this kind of structure is not very stable by itself. So here, because we have guanines, and guanines has 2 rings, what is happening? Pi-pi staking occurs, and it can produce its own charge. So that's why EFM is a useful tool for measurement of this kind of structures. So on the left-hand side is intramolecular quadruplex. On the right-hand side is a tetraquadruplex. So so this molecule shows us way higher and way stronger, like visible EFM signal in positive and negative bias leaf, so it's +4 volts and -4 volts, whereas like the another structure does not show any electrical properties at all. So this is just an example how you can use electrostatic EFM. And another example is related to biolayers. So the electric polarization properties of very, very thin biological layers that are made of proteins, lipids, polarization can also respond to external electric field. And of course, because it's a cellular membrane, it plays an important role in many areas. In particular, this kind of layers are inherently coupled to cell membrane like of, for example, mitochondria and so on. So on the left-hand side, you can see a schematic representation of the whole setup, and then data analysis that was used to determine the dielectric constant of ultra thin bilayer. So the electric constant of the bilayer patches, so this bilayer was used as a small patches as here. So this is the view from the top. And these patches were deposited on insulator substrate. And then the local gradient was measured. So that's what we can see on the right-hand side. So here we see the topography obtained of this single layer patch, and the diameter is about 1.5 micrometer, and thickness, as you can see, is about 5 nanometers. And figure B, the blue one, gives us a dielectric image that is recorded simultaneously. So and then here you have again the dielectric profile here. So these results show us that the dielectric constant of small bilayer patch can be obtained on the insulating materials using electrostatic force microscopy, even though there are a lot of challenges to do this kind of measurements. For example, the precision, how we can measure this dielectric constant is one of the challenges, because even though EFM gives us quite precise numbers, working with biological samples with using EFM is quite challenging task due to the nature of the sample. So this is I would say the last example of group of electric force microscopy. So this is a conductive AFM. So here I compared conductive AFM with KPFM that I already mentioned to you. So both of them, they can be considered like modes of AFM because they are basically operating at a very similar setup. So here is a microfabricated cantilever, and it's exposing at its edge sharp metal and a metal coated tip, and we use it to sense the surface and map its morphology and its electrical features. So it's true for both modes. Even though both techniques, they sense the electrical properties, they work in a bit different regimes. So in conductive AFM, the tip is in the physical contact with the sample, and it allows measurements of the flowing current, whereas the KPFM, its tip passes over the surface without being in the direct contact with it. So in conductive AFM, a feedback loop is used to move the probe along the z-axis, so we can maintain the constant cantilever deflection z. And here we consider the cantilever as a perfect spring, and we control constant force, and everything here works with the Hooke's law. So as a result, the tip follows the contour of the sample surface, and it provides a map of the surface topography. And at the same time, voltage is applied between this conductive tip, and it basically acts as a movable electrode. And what we measure is resulting current. But in KPFM profile, what we're measuring the resulting amplitude. So how we can use this mode? So this is the some of the applications. So here semiconductor nanowires were used. So these nanowires is actually a quite promising material for photovoltaic applications because they have a superior light absorption, and they're very thin as well. So here the conductive AFM was used to map the surface topography and the current distribution of this sample. What we were doing, we're applying the constant voltage between the scanning conductive tip and the sample surface. And the main advantage of conductive AFM is the possibility to access local conductivity information down to really nanoscale. So these are these nanowires. So this is one of the possible applications of conductive AFM. It can be quite useful. Okay, so another type of force microscopy is piezo response force microscopy, or PFM. So it is this mode is a contact mode technique, and it maps the piezoelectric domains. So PFM uses the inverse piezoelectric effect by applying the voltage, and then it uses resulting deformation in the material, and it maps the piezoelectrical properties of the surface. So this method requires a conductive probe and applied AC signal. So the amplitude and phase signals are used to measure piezoelectric orientation, and PFM works on the basis of the converse piezoelectric effect. So a conductive AFM tip scanned across the piezoelectric sample in a contact mode, and so on. And what we can see here, it's like the overall voltage that is applied is direct current plus AC current, and what we can get the tip oscillation at the end, and the PFM amplitude provides the information on the magnitude of the local electromechanical coupling, and the phase images, they give us local polarization orientation. So what kind of curves we can get from PFM? So here, okay, I will go one by one, okay? So when electric field changes from negative polarity to positive, it changes gradually at the point that is known as a coercive field, and it is shown here at the point 3. So the polarization of the sample increases quite abruptly, as you can see here. So this indicates that a number of domains with different dipoles oriented along the field, they can also increase quite dramatically. While we're increasing the field, the polarization changes gradually, and so at the end of the day, these kind of shapes that we can see in the PFM. So this is like the theoretical shape if you just calculate everything, right? And it's like this butterfly structure. These are like more shapes that are closer to the actual curves that you can see, and these are how they look like in the software. And you see that depending on the voltage that you're applying, the shape differs. So I think this is a good example how you can use the force curves to understand what is happening in your sample. So where we can use it, so piezoelectricity is a potential that is induced by mechanical stress in crystalline or structured materials. And many years ago, it was demonstrated different piezoelectric effect in the bone and lung and so on. So here's the example of collagen fibrils. And when we use piezoelectric force microscopy, we can see the different direction of these fibrils, even though on a topographic image we don't see much here. So when you apply these forces to these samples, that they can change the so what you can see is the change of the direction of the fibrils. The same approach is also used for different bone models, because bone has a lot of organic matrix, for example, type 1 collagen, and using PFM it is very handy because you can check the response and elasticity and hardness of the tissue, and then check the mineralization process of the tissue. Okay, but please note that the voltage induced deformation is quite small. It's a picometers per volt, and it's a very small number. And this leads to a very small signal to noise ratio. And how we can solve this kind of situation? We can apply high voltage, but if you put the too large voltage, then you can basically burn the sample. And this is like the example of the burn sample here. And how we can avoid that is to play. With resonance amplification. But again, I just want to. So what I want to say is that the piezo force microscopy sometimes does not give us very good resolution in general, and it's very easy to damage the sample. And the last type of AFM mode of AFM that I want to talk about is the high-speed AFM. It's like the first concept, the first time when it was introduced was about 1991 or so. And why we need high-speed AFM. So the major drawback of AFM in general is the relatively low temporal resolution, because it requires minutes to obtain a single image, and it also limiting force measurements to approximately 0.1 milliseconds. So it was important to develop the high-speed AFM to detect different, for example, biological processes, because it's one of the limiting things is the time in the biological process. So a high-speed AFM allows us to visualize the conformational changes of proteins in real time, and it has been applied for like a number of different biomolecules. So in brief, there are most important elements that allow high-speed AFM to operate in such mode. First is ultra-small cantilevers. So modern microfabrication techniques allow us to get cantilevers about 7 micrometers long, 2 micrometers wide, and so on. And this is probably the most critical point for high-speed AFM imaging, is the reduction of the cantilever sizes and mass, because it will allow high resonance frequencies that we can use to measure the signal. The second one is the fast actuators. So the Z-piezo scanner is driven by high frequency signals during this high-speed imaging, and it will generate mechanical vibrations. So to minimize the vibrations, these scanners are being modified a lot, and the materials that they are made from is also changed. So fast amplitude detectors, the cantilever oscillation amplitude is measured and output by a Fourier method at every cycle of the oscillation, what allows the quite fast detection. And the last one is adaptive and dynamic feedback. So during the fast imaging, the tip tends to detach completely from the surface, especially when you go on the kind of downhill direction. So and this effect is known as a parachuting. And to fix this, people use dynamic controller that consists of a feedback control that increases automatically the gain every time when you move in a downhill regions, for example. And on the right-hand side is a schematics of high-speed AFM system. And so, and the down here is the example of the application. So here you can see a myosin. Myosin is one of the protein that works in our muscles, and the function of this particular type of myosin is a cargo transports in the cell. So it's not in the muscle, but in the cell. So single molecules of these myosin, they move along the actin filament over quite a long distance. And here is just an example of using high-speed AFM to detect the movement of these proteins. So the blue one is the myosin, and you can see how it moves across the actin. Okay, so I have one more slide left, but it's just another application of the high-speed AFM of imaging remodeling process. So this is a protein that is helps to remodel the membrane. So let me just show. So basically, there was a long time ago, there was hypothetical mechanism how this protein works, and then it was confirmed by high-speed AFM. So these are the links that you can read, and now let me just show you the polymerization membrane deformation, how it works. So basically, we have these SNF7 protein is quite small by itself, but then it can assemble and polymerize in a spiral-looking structure. And then once it is formed, it causes the deformation of the membrane. Here you can see how the structure. So this is what was confirmed by AFM. And then it's quite useful because it helps to transport different cargo proteins across the membrane. And then these cargo proteins are getting inside the cell like this. So yeah, this is all for today.
С вами был Тибериус. Если видео понравилось, ставьте лайк. Если видео не понравилось, так уж и быть, ставьте дизлайк. Но обязательно напишите почему. Подписывайтесь на канал. Всем пока. До скорого.